Good morning. I'm Ed Weiler, Associate Administrator for the Science Mission Directorate. I'd like to welcome you to this historic occasion, the day many of us have long been waiting for to celebrate Hubble's new beginning. I'll talk a little bit about that in a few minutes, but for now I thought I would like to bring you back to this past May, when your main question in the media was, when are we going to see the pictures? We know we've had successful spacewalks, but when will we see the pictures? That's why we're here today, to see the pictures, and a few spectra too, I might add. We have many dignitaries in the audience today to help us celebrate this occasion, and Charlie Bolden, the NASA administrator, will formally introduce them in a few minutes. But one in particular has been, in my mind, a full-time Hubble partner these past 2 decades. Senator Barbara Mikulski has actively supported the Hubble mission throughout its long history. She was instrumental in helping to ensure this last servicing mission even happened. And without her long and steadfast support through thick and thin, we wouldn't be here today. I don't think there's anyone here or in the scientific community who would disagree with her being given the title Godmother to the Hubble. We sincerely appreciate everything she's done over the years in support of this mission and NASA overall. And Senator, I have to relate one personal story. You probably remember this, because I certainly do, but I was a younger astronomer at NASA, and I had the distinct honor and privilege to present the senator from Maryland the first images from the repaired Hubble Space Telescope on January 13th, 1994, in a little room in Greenbelt, Maryland. And I was able to give you those pictures and show them to you. And I remember a comment you made when you looked at this one galaxy. Gee, it's like putting my glasses on. And then you took those pictures out and you held them up in front of the press and you uttered that famous quote, "The trouble with Hubble is over." Little did we know how prescient that comment was. And now to another longtime Hubble supporter. It is my pleasure to introduce my colleague and boss, Charlie Bolden, NASA's administrator. As many of you know, Charlie has had a long history with NASA. He's flown into orbit 4 times aboard the Space Shuttle, having commanded 2 of those missions. Charlie's also been involved with Hubble for a long time. He was one of the 5 astronauts who actually launched the Hubble originally in 1990. For several years, he's also served as the chair of the Standing Independent Review Team, which was a critical team of outside experts that reviewed every step of the progress we made toward getting ready for this servicing mission. And that role helped support the decision to go forward with the flight eventually. Charlie has held several technical assignments while at NASA, all of which have helped prep him for perhaps his most challenging position, that is our new NASA administrator. And with that very brief introduction, here's Charlie.
Thank you. Thank you very much. We'll dance. Thank you all very much. Thanks, Ed, for the introduction, and good morning to all of you. It is an incredible pleasure for me to be here to take part in this august occasion. First, Senator Mikulski, I'd like to echo Ed's comments and also personally say welcome to you and to your team that's here. I thank you for being a tremendous advocate and supporter of NASA and an extraordinary champion of our Goddard Space Flight Center in Greenbelt, Maryland. Your energy, enthusiasm, and perseverance are the key reasons that we're here today. It's truly an honor and a pleasure for me to be here with you. Senator, if you don't mind, before I turn the microphone over to you, I'd like to say a few words because Hubble truly has a special place in my heart. Hubble's a teachable moment in unparalleled teamwork. It's the work of thousands of intrepid individuals, including scientists, managers, engineers, support staff, center personnel, contractors, international partners, spouses, at least 2 of whom are here. In fact, I see several, as a matter of fact, who go unheralded, but play a critical role in what we do. And of course, current and former astronauts. And by my count, and Scooter, you can help me here, I think there were 33 different visitors, 33 visitors to Hubble, some of whom went more than once, and they will go unnamed because I don't want anybody to chastise them for their greed. They have been the ones who were involved in putting Hubble into orbit and enhancing its capabilities with subsequent servicing missions. These people are dedicated to the beliefs that space holds tremendous benefits for our lives on Earth, and the noblest scientific frontiers can be engaged from that lofty perch. Frankly, I'm really excited to see everybody here, especially the space shuttle crew that gave Hubble a new beginning after its servicing mission this past May. To Commander Scott Scooter Altman and his crew, well done. Scooter, I can't say enough about the team that you led. And you and your crew, I understand, are going to share some of your thoughts in the next briefing following this. Also here in the front are two of my former compatriots, Commander of STS-31, the Hubble Deploy Mission, Colonel Lauren J. Shriver, U.S. Air Force retired. I had the distinct honor of being Lauren's pilot on the deploy mission of Hubble back in 1990. Lauren, I'm really glad that you were able to be here because it's very special. Mission Specialist Captain Bruce McCandless, U.S. Navy retired, is also with us. And Bruce, I want to thank you for your presence. I'm going to go away from the script here because I want to tell a story about Bruce and one of our other mission specialists who is not here. Dr. Kathy Sullivan was going to be here, and she'll be here later today. But I think it is somewhat appropriate that she is out of the room. And the reason I say that is because a little known secret about the crew was some of you will remember, we had difficulty deploying one of the solar arrays on deploy day. And so what was supposed to be like a 15-minute evolution turned out to be a one-day evolution to get Hubble configured so that we could release it. The decision was made that for contingency, we would put, and Senator Mikulski, you can appreciate contingencies. We put Bruce McCandless and Kathy Sullivan in the airlock, and we started to depressurize the airlock. And if my memory serves me well, we were 5 minutes away from being completely depressed and opening the hatch and sending them outside. When all of a sudden, a young engineer from Goddard convinced everybody that Bruce McCandless knew what he was talking about earlier that morning when we first started having problems, when Bruce said, it's a tension monitoring module. And we all went, what's a tension monitoring module? And he said, it's just some software we put in the satellite so we wouldn't rip the solar arrays apart if we had a problem. Nobody paid any attention to Bruce because most of us usually didn't. Because we knew he was smarter than the rest of us and we didn't want to let him know that. So a young engineer at Goddard later that afternoon said, I think it's a tension monitoring module. And if you will allow me to change some ones to zeros, and I am embellishing this story, Dr. Weiler. It probably didn't happen like this at all. But we were told that the signal was sent from Goddard to NOAP, the tension monitoring module. Immediately, the wayward solar array went out. I floated up because I was the IMAX camera operator, donned my hefty, big IMAX camera and started to shoot as Steve Hawley maneuvered Hubble for its released it, and Bruce and Kathy are going, what about us? What about us? And we said, just hang tight. And so the two people who had probably worked more than anyone else on the crew to get Hubble ready for deployment were locked in the airlock. And they missed the deployment. And in fact, it was like an hour or so later when we were able to go repressurize and let them out. But there are not a lot of people that knew that story. So once again, Kathy is missing from the unveiling here, but I'm certain that'll be okay. Our other crew member who is unfortunately not here is Dr. Steve Hawley, who actually released Hubble from the shuttle's robot arm. He had a previously scheduled Hubble engagement, and we all agreed that that would complement today's event, and so he gets to give Hubble hugs from elsewhere. Hubble's launching marked the most significant advance in astronomy since Galileo's telescope. After almost 20 years of service, our view of the universe and our place within it will never be the same. We're also nearing the culmination of the International Year of Astronomy, a global celebration of the telescopic exploration of the heavens begun by Galileo 400 years ago. I'm sure I speak for all the servicing mission crews, and certainly for my fellow crew members of STS-31 when I say that after almost 20 years of service, we are so proud and honored to have been a part of the Hubble story. We await new chapters being written with a telescope that, following the last servicing mission, is significantly more powerful than ever and equipped to last well into the next decade. Hubble is one of the most accomplished scientific instruments ever created. Indeed, this great instrument has captured the imagination of people everywhere, especially the youth across our great nation and around the world. Everyone knows how important it is to me for NASA to inspire the next generation of explorers. And now, it's my sincere pleasure to turn the microphone over to the one and only, as Ed stated, Hubble godmother, the Honorable Senator from Maryland, our friend, Senator Barbara Mikulski. Senator Mikulski.
Good morning, everybody. I'm really happy to be here with all of you. And as you can see, I very clearly know the difference now between a hard landing and a soft landing. I have one of these great space boots on. I feel like I'm half of an astronaut here. But right after you all landed, so did I. But I took a fall coming out of church. I'm sure God had a message for me. He waited till I finished church before he sent me that message. But I'm very pleased to be here today for this very exciting set of videos that we're going to see for the Hubble New Beginning. I want to thank Administrator Bolden, and it's great to be here at the NASA headquarters. Like Administrator Bolden, I really want to congratulate all of you. The reason we're going to see the Hubble New Beginning is because all of us in this room and many around this country and many around the world have been part of Team Hubble that have helped design Hubble, fix Hubble, launch Hubble, keep Hubble operating. And I want to, like you, Administrator Bolden, pay tribute to them. Of course, I'm very proud of my hometown team, the Goddard Space Flight Center, which is in charge of Hubble's daily operations. I'm very excited about the Space Telescope Institute in Maryland, where Goddard is the catcher's mitt for those fantastic rays that are coming from the telescope, tosses it to the Space Telescope Institute to then translate it into scientific information that goes global. Very few people realize that what we have done with Hubble is one of the greatest forms of public diplomacy that the United States has. People can talk about Fulbright Fellows. They can invite students from around the world to come and study with us, what I really support. But what we do with Hubble and much of what we do at NASA is open and public and given to the world, and the world looks forward to us. When it comes to space, we are the indispensable nation. We thank our international partners for what they do every day and the space station and the wonderful things that they do, but we really are. The information we give really does help with new scientific discovery and scientific inspiration. I want to thank the ground crew at the Kennedy Space Center and the Johnson Space Center, where astronauts train and launch and do all the things that enable them to blast off from the shuttle to go to make sure that Hubble continued to be fit for duty over these long years. And a particular tribute to the astronauts and to the people who love them. And by the way, we all love them for their heroic feats during the many marathon spacewalks, for their patience, their dedication, their duty-driven approach. There were considerable delays, one where we're going to have Hubble at all, and then even during this launch period. So I just want to say, not only on behalf of myself, and not only in behalf of the Senate and the Congress, but I want to say in behalf of the American people, thank you. Thank you, astronauts. Thank you, Team Hubble, because you keep America flying in a way that inspires all of us. Hubble is really important to us and to the world. I've had a long history with Hubble, and it's been a roller coaster ride. When we first heard about Hubble, I heard about it not only through budget memos and where I became the new chair of the VA HUD bill, but I was fortunate to have two space senators, Senator Jake Garn and Senator John Glenn. And they said, we love the astronauts, we love human space flight, but we're going to be doing things in technology that will will change the paradigm about how we think about the universe. Well, I saw the Hubble get launched. I was so excited. Then we waited, and then we waited, and then it was really a fuzzy, fuzzy picture. But steadfast, we launched the new mirror that fixed Hubble. I said it was the most expensive contact lens in world history. In 1993, we gave Hubble a new opportunity. But also, what we demonstrated in installing that new contact lens in space was that by the way the astronauts could do it, they then could do the space station. Had the astronauts not been able to repair the Hubble, we knew that they could not then build the space station in the sky. Well, our wonderful astronauts went back time and time again. 1997, 1999, 2002, each time giving Hubble new batteries and new technology. Then we all know the story. In 2004, Administrator O'Keefe canceled the Hubble and was concerned about the safety of the astronauts. We understood that. But when I reached out to him and said this, when someone gets a terrible diagnosis and they think it's going to be the end for them, they get a second opinion. Would you at least allow a second opinion on the Hubble? And he said yes. Much is said about Administrator O'Keefe canceling the Hubble, but I want to talk about Administrator O'Keefe being willing and open-minded and generous to say, let's have that second opinion. Well, the second opinion said that going to Hubble would be no dangerous than any other mission. I then met with the astronauts and asked them, why do they risk their lives? Because this is a voluntary assignment. They said they wanted to do that scientific breakthrough. Remember that marvelous lunch we had on Capitol Hill with my colleagues? And that's what they did. Well, when I saw this space launch and watched you all yet give it another set of scientific instruments, another set of batteries, I was completely thrilled. But you need to know that one of the great things about Hubble is its inspiration, not only its scientific breakthroughs and information. And I want to tell you a little story that a constituent told me. I watched the spacewalk. I held my breath. I saw you pull the stuff out. I saw you out there for a long time. And believe me, anybody in politics knows what it's like to go for maybe oxygen for a long time and to be tethered. But here's what this constituent told me this story. He has a little boy, 4, that watched with him the NASA channel and all of the walking. He loves mechanical things. And they said, oh, the astronauts are doing this, and they're doing this on the shuttle, they're doing this on the shuttle. Meantime, his 2-year-old sister is walking around, Laurie, like we do. They don't always know what we're doing, but she was taking it all in. So flash forward. There is a senior citizen picnic, but you had to be bussed in. And they said, oh, we'll meet Pop at the parking lot, and we'll go to the picnic on the shuttle. She was very excited, and off they went. So they get to the parking lot. Everybody is duly lined up to get on the bus, and she starts to cry. She doesn't want to get on the bus. She wants to get on the shuttle. This little girl thought she was going to take a rocket ship with her grandfather to a picnic someday, right? This says the impact. You never know what's going on in the minds of these children. And on another note, and I'll really conclude with a story. On another note, one of the things that also inspired me and others was the fact that Dr. Weiler then worked with the Smithsonian to develop an astronomy book for blind children. It has been now published by the Smithsonian. It is, they use the pictures of the Hubble in Braille, the way they can do this. And it's called Touch the Invisible Sky. So to all who had a role in Hubble, to all that enables all children to be able to participate. Today, we're going to see new pictures where, because of all of you, we were able to touch the invisible sky. I'm so glad to have been part of it, and you can count on me to continue to support NASA. We're going to keep forward. It's not about budgets, line items, or memos. It's about science. It's about technology. It's about discovery. It's about our American character and about the future of our children. God bless, and thank you very much.
With that brief unveiling of our images, I'd like to now start the part of the press conference where we're going to get some scientists to talk about what they mean. With me on this panel are 4 distinguished scientists, but they represent hundreds of scientists, engineers, astronauts, and other support people that have worked diligently over the last 30 years to keep Hubble working at its peak efficiency. Now I'd like to introduce them. On my far right, and from the University of Virginia, is Dr. Bob O'Connell, chair of the Science Oversight Committee for the Wide Field Camera 3, one of our new instruments. To my immediate right is Dr. James Green, Cosmic Origin Spectrograph Principal Investigator from the University of Colorado in Boulder. On my immediate left is Dr. Dave LaCrone, a 30-year veteran of Hubble, like myself. He's Goddard's Senior Project Scientist for Hubble in Greenbelt, Maryland. And on my far left is Dr. Heidi Hamel, Senior Research Scientist at the Space Science Institute, also in Boulder, Colorado. Before I hand over the mic, I'd like to say a few words. First, I've been with the Hubble program for about 30 years and have watched the program mature quite a bit. As many of you know, all of the servicing missions were filled with edge-of-the-seat excitement. The world watched as our astronaut team, some 32 astronauts, individual astronauts over the years, worked their magic to keep Hubble alive. And none was more exciting than the last servicing mission, number 4, which is actually number 5, but we won't get into that. The astronaut team, led by Scooter Altman, installed 2 new instruments. What was most amazing to me was repaired 2 instruments that were dead, literally dead. And they took them apart, put some new circuit boards in, put it back together again, how many hundreds of screws, and somehow they brought them alive. As I told some reporter this morning, if they had just fixed one of them, I would have been amazed. They fixed both of them, and you'll see some of that data today. And they replaced gyros, batteries, blankets, and other odds and ends for good measure. Bottom line, these professionals left Hubble as a new state-of-the-art telescope. This is the 5th time now, new beginning. This is the 5th time we've had a new telescope up there, capable of continuing its historic scientific journey for at least 5 more years, and I will bet a long time after that. I was telling a reporter this morning that I'm not good at predictions because I was up here many years ago predicting that Spirit and Opportunity would last 3 months. And that was 5 years ago. So as you saw in the unveiling, the instruments aboard Hubble are capable of taking amazing images, and the world stands ready to see what we can do from this point on. And let there be no doubt that this is truly a Hubble's new beginning. With that, I'll turn to Bob to tell us what he's got.
Thanks, Ed. Let me first say that we couldn't be happier about the way things have gone. You recall the installation of the wide field camera was a little touch and go, but I'm happy to say it's working beautifully at the moment. It's working even a little better than we expected. Right now, it's scheduled to be used in half of all the Hubble observations over the next year, and we think a larger fraction over the next 5 years. So we really want to thank the wonderful crew of Atlantis for what they did for us, and especially John and Drew. I think it's safe to say that never have so many scientists owed so much to 2 guys who fixed a stuck bolt. Thank you very much, guys. We have 4 pictures for you today. We're going to show these in order from old age to youth, but it's good to keep in mind that astronomers think that something that's 1 million years old is young. So let's start with the first picture. This is a picture of a gigantic star cluster in our own galaxy. It's called Omega Centauri. It contains about 10 million stars, and we're only seeing a very small piece of it here. These are all old stars. They're about twice as old as the sun. And you can see they fall into 3 different color classes. They're gold stars, and in fact, most of the stars in the image are gold, and that's the color of the sun. But then there are very blue stars, and there are very red ones. Now, the color contrast here is real, and it's picked up by our camera. The blue stars are very hot. They emit most of their light in the ultraviolet part of the spectrum. That's one of the new bands we have on the camera, but very little in the red band. And the cool stars are just the opposite. They emit a lot of light in the red band, but very little in the ultraviolet. So just by looking at the colors of the stars in this kind of picture, you can sort them by temperature, and in this particular case, it also means sorting them by evolutionary state, because the temperature differences here are caused by differences in the internal structure of these stars and in the kinds of fuels they're burning deep inside of them. So by studying pictures like this, we learn about the physics of stars as they approach very, very old age. Now, the second picture is called the Butterfly Nebula for obvious reasons. It looks like a butterfly. This is also a star in old age, but it's gone beyond the stage of the stars you just saw, and it's now beginning to lose its outer envelope of gas, which is drifting back off into space. And that's being lit up by the radiation from the collapsing star that's left behind. Now, in this picture, we took advantage of the special filters on the new camera to isolate the light of 5 different elements, and they've been color-coded separately here. So, for example, the red in this image is nitrogen, gas, and the blue is oxygen. Now, what you're seeing here is a critical phase in what you might call galactic ecology. It's the point at which material that's been chemically processed inside of stars is returned back into space, where it can form new stars, new planets, and in fact, life on many of those planets. In this particular kind of star, much of the carbon that is in our bodies and in other life forms is produced and recycled into the galaxy. The third picture is the only one of something outside our galaxy. It's a group of other galaxies that is called Stephan's Quintet. It's about 300 million light years away. Now, the name comes from the fact, as you can see, there are 5 bright galaxies in that field. 4 of them are actually close together in space, but the 5th one is just accidentally along the line of sight to the others. It's nearer to us, and you can tell which one that is thanks to the beautiful resolution of the camera, because it's the one in the upper left here in the picture, the blue galaxy. You can see the individual stars in that galaxy thanks to the camera. The other galaxies are 8 times farther away, and they're too far away to see the individual stars. Now, all of the blue stuff you see in this picture is young by our standards. That means it's between 10 and 100 million years old in this case. The 4 yellowish galaxies you see in the frame are gravitationally interacting with each other. They're pulling together, and you can see that material has been pulled out sort of like taffy from some of these, and there's a spray of blue stars right in the center there, which has been produced by the fact that one galaxy is running into another there. This kind of an interaction is a normal step in galaxy building, and we expect that over time, long stretches of time, those 4 galaxies will eventually merge into a single big galaxy. Now for the last picture, we're back in our own galaxy. This is a cloud of dense material which is being bombarded by radiation, intense radiation from surrounding stars. You don't see the surrounding stars, they're out of the field, but they're bombarding the cloud in the center. And that radiation is having 2 effects. First of all, it's evaporating and even disrupting the outer parts of this cloud. And that's what produces the filamentary structure you see there, the green and the blue colors. And at the same time, the radiation is compressing the cloud and inducing new star formation inside of it. We call this triggered star formation, and it happens all the time. Now, the young stars that are being formed there you cannot see in this picture because in this particular color band, the cloud is opaque. But if you go to the new infrared band that our camera provides, you can see inside the cloud. And so if we could go to that, this is going to be a dissolve from this picture, which is taken in the normal visible bands, to one taken in the infrared. And what you'll see is that the cloud disappears to a kind of ghost-like appearance. You see lots more stars. 4 of the bright ones in the direction of the cloud are young stars inside that cloud. And one of them, the one more or less in the center of the picture, has these jets coming out of it. You can see these beautiful long jets coming out. That's material being blasted out at very high velocity out from what's going to be probably a planetary system by the time this thing settles down. And we only see these kinds of activities in stars that are about 100,000 years old. So what you're seeing here is a very energetic infant star being formed deep inside this cloud. Now, based on these pictures and the other data we've gathered so far, we're fully confident the camera is working as it was intended to work, and we're eagerly looking forward to see what other astronomers are going to do with it over the next 5 years. And now I'll turn it over to Jim Green, who's going to tell you something about a different dimension of capability with Hubble.
Thank you, Bob. I'm going to present the first results from the Cosmic Origin Spectrograph, the other new instrument that was installed during servicing Mission 4. The Cosmic Origin Spectrograph, we like to call it COS, doesn't take pictures in the usual sense. It's a spectrograph and records the spectrum of light from objects, breaking that light up into its constituent colors, much the way a prism makes a rainbow, but with much greater precision so that we can actually make quantitative evaluations of what the physics that's going on in the objects we look at. Now, because every element and every chemical compound in the universe has a unique spectral signature, it absorbs certain energies of light and doesn't interact with other energies of light. When we measure those energies of light, we can tell what chemicals are present, where they are, how hot they are, how fast they're moving, and we can see the physics of the objects that's going on, as well as the physics of the gas that the light might pass through on the way traveling towards us. As an example of this kind of observation, my first slide is a spectrum of a quasar known as Parkes 0405. This object is about 7 billion light years away, and so even at the resolution of Hubble, it just looks like a dot. Okay, but it's really a giant galaxy, probably with a giant black hole in the center and millions of stars worth of material falling into that black hole, creating an enormous amount of light. But it's so far away, it's just a dot. But when we take a spectrum, which is the red line shown there, and the variations are all caused by different chemicals in the quasar and different chemicals along the line of sight towards us, we can begin to understand the physics that's going on here. For example, we've listed down there IgM filament 1 and filament 2. That stands for filaments in the intergalactic medium. We believe that most of the matter of space in the universe is actually in wispy filaments in the voids between the galaxies, but they don't make enough light to be seen by taking a picture. They have to be inferred their existence by their effect as the light travels through them, and that's what we're seeing here. And we're not only seeing hydrogen, the most common element in the universe, but we're seeing oxygen as well. And in fact, not labeled here, we also see things like carbon and nitrogen. And so the elements of life are being produced in stars like the picture we saw earlier, but they're also being distributed throughout the cosmos, and not just locally, but even into intergalactic space. And this is one of the great mysteries we have currently about understanding the cosmos, is how do these get so far away from the stars that actually produce them? Now, The great new ability of COS that we brought up here is that this spectrum was taken in less than 1/10 the time it would have previously taken with Hubble. The new instrument is 10 times more sensitive, which means we can look at 10 times as many targets, or alternatively, a target that's 1/10 as bright, and get that science. And what that means is we can start to build up a catalog of the locations of all these wisps of gas through the intergalactic medium. And instead of having a handful of such observations, we're going to have hundreds, even thousands of such observations. And we're going to be able to start to build up a map of how matter is distributed in the cosmos. And this is one of the most fundamental questions we have about the nature of the universe, is how did matter wind up structured through the universe the way it is? It started out smooth. Today it's very clumpy. It's mostly in stars and galaxies that we see. How did it get that way over the evolution of cosmic time? Now, the second image we have is a spectrum taken of a supernova remnant in the Large Magellanic Cloud. And so this is a star that exploded, and the wisp, the picture in the upper corner was taken with wide field camera 3, and the bright little rings represent outflowing gas from the exploded star. And we looked at a particular knot that we know had a lot of oxygen in it and took a spectrum of that, and we're able to actually identify then the amount of oxygen and carbon, and also it's not labeled here, but silicon in the system. And this tells us about the chemistry of how these stars explode, how the matter gets distributed between them. It even tells us about how the star operated prior to its explosion, because the explosion occurs in the winds that the star blew out beforehand. So all that interacting, we can start to understand that physics, and once again understand how did these chemicals congregate eventually into planets and life, and questions that we're all concerned about. Finally, my third image is of Markarian 817. It's a nearby active galaxy. An active galaxy means that the light coming from this galaxy is predominantly coming from something other than just the stars in the galaxy. There's more light being produced by some other physical process than by all the stars put together. And again, we assume that that's a black hole at the center of the galaxy with enormous amounts of material falling in, heating up, making a lot of light, and a small amount of it being shot out as jets and as globules, just the way the gravity interacts in these processes. So what we show here is a spectrum that was taken in 1997 in the blue line with the Goddard High Resolution Spectrograph, which was the spectrograph on board Hubble at that time, and in 2009 with COS. And you can see the spectra look pretty much the same. One of the things we wanted to do was to calibrate the instrument with this observation and make sure it was working properly. But this observation took only 9% of the observing time that it took in 1997. So again, we've become a much more powerful instrument and able to get much more data. Also, that's the entire spectrum from 1997, but that's only 1/8 of the spectrum that we collected in 2009. It runs off the page 4 times as long in both directions. One of the interesting things to note, as denoted there by the red mark, is that one of the features in the spectrum in 1997 is now absent. This was a blob of gas blown out by the black hole that the light was passing through that has now since moved out of the way, and in fact, it is no longer visible to our instrument in this time. And I just think it's sort of interesting to note that we're looking at something millions of light years away, the size of a galaxy, and yet over 12 years we can see how it's fundamentally changed. And that the cosmos, even though it's billions of years old, still operates on human timescales. I'll just wrap up by saying that the goal of COS was to build an instrument 10 times more powerful than the previous capabilities. And I'm pleased to announce that we've succeeded in that goal, and I'm looking forward to getting lots of observations in the next coming years, and I agree with Dr. Weiler that we've got a good 10 years to go. But with that, I'll pass it on to Dave Leckrone, Senior Project Scientist for HST.
Thank you, Jim. Good morning. Bob and Jim have described some of the early observations acquired with our 2 brand new instruments, which extend Hubble's observing power by factors of 10. And these are very high technology instruments and are performing superbly in both cases. Another unique aspect of this mission, however, was the attempt to repair 2 very valuable instruments, very valuable assets that had failed electronically. Space Telescope Imaging Spectrograph, which failed in 2004, and the Advanced Camera for Surveys, which failed in 2007, in both cases because of electronic short circuits. So a bold initiative was undertaken and involved tremendous effort on the part of the crew working with our engineers and designers on the ground. A bold initiative was undertaken to attempt to repair both instruments. And I agree with Ed, going into the mission, we realized we were attempting 2 repairs. If we could get at least one of those to be successful, then that would be a good outcome for the mission. What we really never dared dream of was the possibility that actually both repairs might work. So I'm here to report to you today that both are working splendidly, and I'd like to show you observations taken since the servicing mission with both of the repaired instruments. So if I may have the first graphic, please. Okay, what you see here is a representation of two different observations. On the left, there's a picture of an image taken with Hubble many years ago of an exploding, a very highly active star called Eta Carinae. And this star is actually two stars, very massive stars orbiting around each other. In some cases, one's in a highly elliptical orbit around the other, and they come close to each other. These stars are so massive, they burn their energy very rapidly, and they're not going to last very long. Their lifetimes are short. Sometime within the next 100,000 years or so, this system of two very massive stars is going to blow up. It's going to become a massive supernova, possibly a gamma ray burster. It's going to be an intensely energetic object, and it's only 7,500 light years away from the Earth. The nice thing is, at that distance, we think we're protected, so we don't have to worry too much about the impact. But astronomers within the next 100,000 years or so are going to have the opportunity to observe, and ordinary people are going to have the opportunity to observe an extraordinary flash of light in the sky and to study it. Now, what you see coming off to the right there is the new observation with the Space Telescope imaging spectrograph. There's that long dark slit that you can place over the image of the object, and you can collect light point by point along that slit. And at each of those points, the light is spread out into its component colors, and you can see a spectrum that corresponds to each spatial point along the slit. And in this particular case, this was taken last June. The two stars had just passed through their moment of closest approach, and there was a lot of energetic activity happening. I talked to Mike Massimino and the rest of the crew before the mission, and I said, one of the things we really need to do, we've been monitoring this baby, it's so dynamic, it's so energetic, we've been monitoring this since 1997, and then we had to stop in 2004, and we haven't been able to continue the story. And so now, in fact, thanks to you guys, we're back up and running, and the story continues, and we can continue to monitor how this star is changing over time and look at its dynamics and get some understanding of how someday in the future this is going to become a really spectacular fireworks show in the sky. So that's the Space Telescope imaging spectrograph story. The next image, please. Okay, this is a cluster of galaxies called Abell 370. It's about 5 billion years away from us. It's a group of galaxies, large and small, that are all gathered together and held together by gravity. In particular, they're held together by the gravity of dark matter that's within the cluster. It's not just the luminous matter in the galaxies you see, but there's about 5 times more material that's cold dark matter that we don't really understand what it is. But all this material together exerts enough of a gravitational force that it can bend light, as Einstein predicted in his general theory of relativity. So the light from galaxies that are beyond this cluster, the light rays are bent as they pass through the cluster and come to us, and they're focused like a crude lens. So this is called gravitational lensing. This particular cluster was one of the early examples of this that astronomers came to understand as an illustration of how Einstein's gravitational lensing works. And in fact, you see that long bright arc up in the upper right. It was known back in the 1980s that that was an example of a gravitational lens. The power of Hubble, though, is that we can see incredible detail in that arc. So if I may have the last image, and it's rotated 90 degrees, and we've zoomed in. So this is really fascinating to me. I've never seen anything quite like this before. This is the gravitationally lensed image of a single spiral galaxy that's like twice as far away from us as the intervening cluster. And so and we call this the dragon just because it kind of looks cute in that sense. But on the left side, you see an image of the galaxy, quite detailed with a lot of color information in it that we'd never seen before we had taken this image. And then up on the upper right, you see an image, the tail, so that's the head of the dragon, and then the tail in the upper right, which is an image of the very same galaxy. And in between, you see the stretched out band of light, each which really is comprised of stretched out images, 3 or 4 additional images of this same galaxy. And this is what, it's just remarkable what gravitational lensing can do. And in particular, this is nature's telescope. This is taking the power of Hubble and enhancing it tremendously with gravitational lensing so that we can actually study detailed structures in galaxies that are incredibly far away. Another thing I can say is we don't see, normally you might see a counter example of this on the other side of the cluster. You don't see that, and that tells us the very particular special way that the dark matter is distributed within that cluster. So I'm proud to report that prior to this mission, with our instrument failures, we were down to 3 operating channels, instrument channels on Hubble. Today we have 13. We have 6 fully operating instruments today. I say fully operating. One of them, the NICMOS, has just come back online. We're still in the process of checking it out, and it'll begin its science program a little bit later. But in addition to the instruments, I'm not able to report any failure or problem on the spacecraft itself. So I know it was a tough mission, and I know there are a lot of travails, but somehow, some way, you guys pulled it off. You just refused to say die, and you kept going. And we have a fully functioning, beautifully operating Hubble Space Telescope today. So with that, I'd like to turn it over for some closing comments, or nearly closing comments, to Heidi Hamill.
Thanks, Dave. It is a wonderful coincidence that servicing mission 4 occurred in 2009 because, as Administrator Bolden already said, 2009 is the International Year of Astronomy. This is the year we celebrate the 400th anniversary of Galileo turning his telescope to the skies and revolutionizing our understanding of the cosmos. The Hubble Space Telescope, in a sense, represents 400 years of technological innovation. Hubble's contribution to astronomical research is its ability to provide truly unique observations. The new equipment installed during the very successful mission by the astronauts not only restores Hubble to its full operational mode, Hubble's new cameras and spectrographs propel us forward into a new beginning for astronomy and astrophysics. Hubble's new capabilities were tested quite dramatically and unexpectedly just 7 weeks ago. 7 weeks ago, we got a report in the middle of the night that something had hit Jupiter. And once we convinced ourselves that that was in fact correct, all telescopes around the world turned to Jupiter. And the question that I grappled with was, well, what about Hubble? 15 years ago, exactly 15 years ago, when a shattered comet, Shoemaker-Levy 9, had crashed into Jupiter, Hubble was at the forefront of the observations, and I had been at the helm of the Hubble team. So, could we do it again? The trouble was that the astronauts had just finished their servicing mission, and the Hubble team was deep into what they call SMOVE. Servicing Mission Orbital Verification. And this orbital verification is an extremely important part of the mission. No science is being done, but all the instruments are being checked, calibrated, exercised so that we can make sure that the telescope is fully functioning and well understood so that when they turn it over to the astronomers, they get the good data that they really want to do. And interrupting orbital verification, not a good idea. Words like impossible, inconceivable were bandied about. So I was asked, well, what is it that Hubble and only Hubble can do? And I responded, high-resolution visible imaging, ultraviolet imaging, only Hubble can do that. So we got approval for the time. Obtaining it was really, really difficult, but they did do it, and kudos to everybody involved in that. Now, in August, we released a small snapshot showing the impact site, and if we could show that to the people here. And there you can see the black clouds that were created during the explosion when this object hit Jupiter. The details in this image far surpass anything that we have been able to obtain from the ground. We just got our last set of images yesterday, so I haven't even seen them yet, so I can't show them to you yet, but I do have something I'd like to share with you, and that is Hubble's view of the full disk of Jupiter in glorious color. This image is our highest resolution image of Jupiter since 2007, when the New Horizons mission flew over the cloud tops of Jupiter. And you can see the impact site down in the bottom there, but you can also see fantastic structure and detail across the rest of the disk. this was an extremely challenging observation to make. It was tuned for science, not for public release. And so Michael Wong at the Space Telescope Science Institute had to do a tremendous amount of work to be able to recombine our different colored filters into this beautiful image, but it's fantastic. Now, this illustrates a superb aspect of the revitalized Hubble, and that is its wide field imaging capability. This is something that all of us are really going to be taking advantage of, is the ability to get very large pictures. The color composite also talks about the different kinds of colors that we see. This is made with visible wavelengths, red, green, and blue, but we also have some fantastic ultraviolet and near-infrared data that we will be analyzing in great detail. More broadly speaking, the true power of Hubble lies just in the creativity of the collective minds of our community. As this final image, which is a montage of the images that you've seen before, illustrates, every field of astrophysics, whether it's our local neighborhood of planets, nearby stars and their attendant planets, galaxies, clusters of galaxies, out to the edge of the universe, every field has questions that are awaiting the power of Hubble. The brief descriptions of the science that you heard earlier, they just barely scratch the surface of the science we're going to do. You're only getting the tiniest taste of what the astronomers are planning to do with Hubble over as many years as it can last. We in the community are already starting to get our data, and we're giddy with the quality of the data that we have with this new telescope. We're especially excited to have the spectroscopic capability restored to Hubble. Hubble spectrographs, and I can say that in the plural now, they permit us to work on a mind-boggling array of scientific questions over a huge range of sizes. As you heard, we're talking about atoms and molecules and how they combine and interact with their environment. But we're doing that on scales that are, dare I say, astronomical. So again, we are entering a new era of astronomy. Hubble's new beginning is just setting the stage for what's going to be coming, including the next great space observatory, the James Webb Space Telescope. With this new beginning for Hubble, we can now see more clearly and understand more deeply the processes that create and shape and drive change within our universe. Hubble is back in action. Together, NASA and Hubble are opening new vistas on the universe. And I'll turn it back to you, JD.
Thanks, Heidi. Well, it's time now for our question and answer session. And before we begin, just a few caveats. If you would, wait until we get a microphone to you. Please identify yourself and your media affiliation before you begin. And if you would, tailor your questions to a specific panelist if you can, to avoid any confusion in that. And with that, let's start with Seth from AP. It's on.
AP. Actually, for Dave, one question with a follow-up. These all seem to, as you said, all except for one were in our galaxy. How far, what is the deepest you've looked so far? How does that compare to how far you expect to be able to look now and how far you've been able to look in the past?
Yeah, I can't give you a really quantitative answer to that, but I'll do my best. We have a program that is about to begin, which it's another ultra-deep field, this time in infrared wavelengths, that will probe as deep as we're able to probe. I'm not sure of the status of that, but it's imminent to its beginning. But what we all have noticed in these images, again, is you take an image of a Stephan's quintet, or you take an image of one of the other objects that we looked at, and off in the background there's all this stuff. There are marvelous details, including going down to small unresolved red blobs. And we know those small unresolved red blobs, in some cases, not in all cases, are distant objects. Now, they're not nearly as distant as we're going to be probing with the ultra-deep fields, because these are relatively short exposure times. But you can already see remarkable differences between what we're seeing now and what we saw with the prior instrumentation, just in this ability to see, oh, look what's in the background. My goodness, I didn't realize that was there. So it's not a quantitative answer, but it says that we're really sensitive, maybe even more sensitive than we thought we were.
Okay, thank you. And to follow up, maybe for Heidi, given the bigger picture, especially the two beauty shots of the Edicorena and the butterfly, you see these sort of glows, this backlit glow that you almost seems heavenly in a way. Uh, One, can you just I for someone who keeps looking at these type of images, does it lose the magic and the luster for you, or how beautiful is this to someone like you who watches us all the time? And just the glow, what is that? Because some people might see a little bit of uh, might find some spirituality in that.
I don't think we ever lose the awe and wonder. I mean, I've looked at hundreds of pictures of Jupiter, but when I saw the first images of Jupiter come back from this impact site just a month ago, all we could say was, wow. You don't lose the wonder. You don't lose the glory. The beauty is there to be appreciated in each new image that comes down with Hubble. And as we use Hubble over the next many years, looking at things that we haven't seen before, with our new cameras probing deeper than we've seen before, there'll be even more wonders for us to look at. So I think it's fantastic. We're not losing. You don't get jaded. You just keep being enthralled with every new image.
Thanks, Heidi. Real quick caveat to the briefing. My apologies to the STS-125 crew. We are going to go a little bit long, but we will get you on here. Also, we're probably going to have to limit follow-ons because of the number of media that we have wanting to ask questions. And finally, to the panelists, if you would, try to keep your brief answers as brief as possible. You can't answer the question, but try to hold it down if you can. And with that, any other questions here in the audience? All right, Joel here in the front from the Washington Post.
Yeah, quick question. Joel Achenbach with the Washington Post. Ed, with this mission being so tremendously successful, this servicing mission, is there any new impetus for serviceable telescopes, particularly with the Augustine Commission looking at some new ideas for the strategy ahead involving this deep space capability where you might be able to go out to 1,000,000 miles out?
All right, well, all we've got so far is executive summary for the Augustine Commission, so it'd be premature to comment. We're waiting until we get the full report, and then we'll be working with the OMB and the Office of Science and Technology Policy of how we would respond to it. But ultimately, now I'm not speaking specifically about the Augustine Commission, but ultimately, if you're talking 20, 30, 40, 50 years from now, I mean, in this century, we're going to have the capability of finding a planet that we can say has life on it. There's no question we have the technology to do that. The trouble is that takes very large telescopes, perhaps even interferometers. And I have my gut level, my own personal opinion, not speaking for NASA now, is that the way we're going to build those new telescopes is probably assemble them in deep space, because you want to be far away from the Earth. So, there is a future for construction, of large things in space, but it's a long way down the road. And we'll have to see how, the Augustine Commission comes out and whether that's part of the near term or far-flung future.
Thanks, Ed. And now we're going to our field centers in Houston and Texas for Media Reporter.
Hi, Robert Perlman with CollectSpace.com with a question, I think, for David. You mentioned an ultra-deep field coming up, but can you give a preview as to what other images might next be coming? I guess Hubble's supposed to support the L-cross impact. What other targets are on the horizon?
Yeah, we have just begun the process of doing science with our newly recommissioned instruments, and we're in what's called Cycle 17, which is approximately a year long, and it's a pre-selected, peer-reviewed, scientifically excellent observing program. So what I can tell you a little bit about there is that, for one thing, we're all interested in Pluto and is it a planet or not, and we know that there's a whole population of Plutoids Pluto-like objects out in the Kuiper belt beyond the orbits of Neptune and Pluto. So we're going to be doing a large survey to try to understand more about our own outer solar system. We certainly are going to be using the Space Telescope imaging spectrograph and the Cosmic Origin spectrograph and the NICMOS when it comes back online to continue looking at the atmospheres of planets around other stars. We had shown some success in coming up with information about the chemical composition of exoplanets, and we're certainly now well postured to push that forward. There's almost no area of astronomy. I mean, I can't cite the Cycle 7 observing program off the top of my head. That is online, by the way, at the Space Telescope Science Institute website, if you'd like to see the whole rundown on them. But all I can tell you is that there are particular themes for which the door was opened by prior Hubble observations, and now we're well postured to walk through the door. And the exoplanet atmospheres is an excellent example of that.
Thanks, David. Now we're going to go down to Florida with the reporter at the Kennedy Space Center.
Hi, everyone. It's Bill Harwood with CBS News, and I'll ask this question to any of you, and it's the question that you get asked every time there is a Hubble news conference, but I'm going to ask it one more time, which is, with the new capabilities that HST now has, how does Hubble fit into the firmament of major telescopes on the planet and elsewhere? In other words, the big monster scopes that are coming online downstream. Where does Hubble fit in with all of those guys with the capabilities you now have? Thanks.
Well, physics rules, and I'll pass it to Heidi, but physics rules. We have an atmosphere to look through. Okay, there are ways to mitigate the atmosphere called adaptive optics, where you have rubbery mirrors which try to correct for the atmosphere. The trouble is you can do that, you can do it very effectively. These large telescopes will have better resolution than Hubble, but over very, very tiny fields of view. I cannot, unless somebody can correct me here, I cannot conceive of taking a picture of the Eagle Nebula with adaptive optics and getting the resolution that Hubble has. Ultimately, as the telescopes get to be 10, 20, 30 meters, they will have more light gathering power than Hubble. They'll be able to go deeper. But then we've got something up our sleeve called Jim Webb Space Telescope, which will start the race all over again.
The other thing that Hubble can do that can never, ever be done from the ground is imaging in the ultraviolet and imaging in some of the infrared, near-infrared wavelengths of light, because our Earth's atmosphere absorbs the photons before they get to the surface of the Earth. So you could make a football-sized field telescope and you'll never collect the photons because they aren't there. So Hubble is absolutely unique, and we must have a telescope in space to complement the very large telescopes on the ground. Hubble is absolutely unique at those wavelengths. Nothing else can do it.
All right, we're going to stay out at Kennedy right now.
Hi, it's Peter King at CBS News Radio, and I guess I'll ask this of Dave Leckrone, and this is kind of a big picture, projecting ahead by maybe 100 years. When we have some of those bigger, better telescopes, maybe that are built millions of miles out in space, how will history look back on what Hubble has done in its first 25 years or so?
Well, of course, we need to be humble, and we need to, but in all humility, I truly believe that Hubble has fundamentally changed the course of modern astronomy and astrophysics, and is taking it in new directions. And new discoveries will reorient the path of science in other directions. But I think we have basically, I'm struggling for a word. We basically have shoved aside the old textbooks and the old concepts of the universe we live in that were based entirely on this distorted view that we had through the Earth's atmosphere. And we have laid a foundation of clear vision that is the starting point from which all future UV optical and near-infrared astronomy will proceed. And 100 years from now, people may have forgotten what we did here in this place and in this time, but that doesn't change the fact that we did set the course of research on its path.
All right. Any other follow-up questions here we'd like to ask? All right. Having none at the field centers as well as our telephone bridge, we'll now go to Ed Weiler for closing comments.
Okay, I'll keep this short because we're over time, but Just wanted to reminisce a little bit. We've come a long way since 1990. I woke up this morning, I felt like I was in the Groundhog Day movie, because we've done this 6 times before. That is, press conferences after SMOV-type periods. The first one wasn't so pleasant. It was June 27th, 28th, 1990, and we had announced spherical aberration and an optical problem. Many people inside the Beltway and outside the Beltway said we should just cancel Hubble. It was a waste of money. We never would have achieved what we said anyway. We said we had a way to fix it, something called the Wide Field Planetary Camera 2 with corrective lenses, as the senator likes to talk about, and something also called COSTAR. Nobody believed, well, very few people believed that it could be done. But the Hubble team of center people, astronauts, etc., proved them wrong in December of 1993. And our redemption day was that day, January 13th, 1994, when Hubble began its new life. Since then, we've had 4 other servicing missions. Basically, Hubble has gotten better and better and better. What Dave and I 30 years ago or 20 years ago said, that for those first press conferences, the promises we made, those look conservative compared to what we've actually accomplished. And it took thousands of people to make that happen. And especially, I have to give special notice to 32 people who kept this from being orbital space junk, which it would have turned into. And those are the 32 astronauts that have flown up to Hubble and risked their lives to keep us scientists very, very happy. And just a few more thoughts. I'd be remiss if I didn't recognize another colleague that's been instrumental along the way, my friend Dave Leckrone. Although we haven't always seen eye to eye, who does? Dave has spent 30 years, like I have, actually more than 30 years, both of us, working for Hubble. He, like I, gave up a research career early in our lives and decided would rather work for the government, for the exorbitant salaries, obviously, but really to really enable other people to do research. So that was something we gave up, but I don't think would ever change the way we progressed. And Dave is going to retire in a couple of weeks, and I'd like to thank him on behalf of the entire science community for your service to the science community. So thank you, Dave.
Thanks, sir.
And one last thought I wanted, or 2 last thoughts. Hubble has inspired not just astronomers, but people of all ages, from young school kids to senior citizens. It has become a scientific icon. It's almost become a cultural icon. You see it on the walls in movies. You see it if you watch Star Trek Voyager. It was splattered all over the main deck. Why is this? Why has this become such a cultural icon? This is one person's theory. Most of us humans, certainly many of us humans, will never travel to some of the exotic places physically that we see in Hubble. But what Hubble has done, it's enabled our hearts, our minds, our spirits to travel throughout the solar system, even billions of light years, to the very beginning of time almost. And I think its ability to inspire at least some of our school kids to consider careers in engineering and science and math, that will be its most important legacy, not just keeping us astronomers happy. And what's next? In 2014, NASA will launch the James Webb Space Telescope that will continue Hubble's scientific tradition for the foreseeable future. Hopefully, both of them will operate for many years beyond 2014. The bottom line, though, is NASA will remain at the forefront of the scientific exploration of the universe. And with that, we'll close today's news conference. Thanks for coming.